In this sample 25, we'll see the boxed plate girder section in SACS. This sample involves elastoplastic flexural buckling analysis of members with boxed plate girder under a compression load. So we will see there will be a boxed plate girder and we will apply the compression load. We will see how the elastoplastic flexural buckling analysis is happening. So in the next page, we will show the figure 106 illustrates a simply supported column subjected to axial compression load at one end. The column is restrained against torsion at both ends and has a small imperfection in the form of midpoint perturbation as a lateral dislocation. And this model consists of two elements with 8 subsegments per members, and material properties are set to SACS default values. Both sub-incrementation option SI and collapse option and arc length method in collapse option are utilized for this benchmark. The analysis carried out 3 boxed plate girder sections with height to width ratio of 1.5 1.752 as shown in the below figure. The figure 107 compares the lateral displacement at the midpoint of the column. Here we will see this end that's fixed for torsion, this end also fixed for torsion, and this roller actually moving. So we have applied the axial compression load and length is 10 meter and elastoplastic buckling analysis we will see it. This H is height and W is the width. So side plate thickness 2.5 centimeter and flange thickness 3 centimeter, web thickness 1 centimeter we are given, and width is 40 centimeter. So we will make 3 analysis with 3 different sections, H by W ratio 1.5, 1.75 and 2. So in this analysis we can see this midpoint lateral displacement versus axial load. So once axial load is increased like this, axial load we are applying like this, it will start increasing it, then midpoint laterally it will displace. The displacement is given here, midpoint lateral displacement for different H by W ratios. Here you can see this blue H by W ratio, that means H by W is 2. That means like if more height less width. H by W ratio is 1.5 means height is less compared to the width, right? So that is having less displacement as compared to H by W ratio 2 has, for the same 50 displacement, it has more axial load. It can take more axial load for 50 centimeter lateral displacement. H by dW when height is more, then it is taking more load for the same lateral displacement. So H by W ratio 2.0, you can see for 50 centimeter it's taking maybe roughly around 4,000 above. It's almost here, almost less than say 3,800 or something. It's coming. You can see exactly how much it's coming. It's coming around 2,800 something, and here it's coming 3.1 something. It's coming. So H by W ratio, if it is more, it's giving more axial load. It's taking more axial load. This is the example for plastic contour of boxed plate girder, bottom compression of boxed plate girder sections buckling.